So here's a scenario presented to you. I would like for you right now to pause the video, read through the question, and decide which inference procedure we should use for this question. So give it a pause, come up with that procedure, and then come back and we'll talk about which one is the correct procedure and why. Okay, so by far probably the most common wrong procedure that will be done on this is a two-sample t-test. You can hopefully recognize that we have quantitative data, so we're going to be talking about an inference test for means of some sort. So that's going to make it a t-test. And at first glance, it looks like we have two groups. We have a before group and an after group. But remember, for a two-sample test, one of the conditions that has to be met is that the two samples have to be independent of one another. And if you actually are taking the time to check that condition instead of just writing it down and saying, oh, it's checked, you'll recognize in this case that we don't really have two groups, right? The before group and the after group are really the same 10 people. We have all 10 of those men in the before group and the same exact 10 men in the after group. So the two groups are in no way independent of one another. So this is not a two-sample t-test. In fact, what's happening here is that for each individual, we have a paired set of data. We have a before and an after pulse rate for each individual. So what we have here is a paired test, sometimes called a paired t-test, sometimes referred to as a matched pairs t-test, and you'll hear me use those terms interchangeably. So I'm going to walk you through the mechanics and top to bottom from hypotheses to conclusion for how to do a paired t-test. So as with every hypothesis test we do, our first step is going to be to write our hypotheses and then to define any variables that we're going to use. So in this case, what we have is we're going to look at the average difference in resting pulse rates for all men. And it's not a bad idea here to indicate which order you're going to subtract in, because you really can subtract in either order. And we're doing the average change because what's happening is in this table right here, for each individual, we're going to actually create a third column essentially, which is the difference or the change in pulse rate, where we do the before pulse rate minus the after pulse rate. So what we're really going to have here is essentially one single column of data. So the mechanics of this are going to actually be just like the mechanics for a one-sample t-test, because we're essentially creating a single sample by subtracting those two values, the before and after, for each individual. So we're going to talk about the overall average difference or different change in pulse rate for all men. So we're going to hypothesize that there is no difference whatsoever in the before and after, that average is just going to be 0. And then the question asked for, is there sufficient evidence that this kind of exercise can reduce resting pulse rates? So since we did before minus after, a reduction would mean that the difference would come out to be positive because the after would be smaller. So our hypothesis then is that the average difference is then going to be greater than 0, which would mean that the before was higher than the after. So those are our hypotheses. And then our next step is to go ahead and check the conditions for the procedure that we're going to run. So our conditions are as follows. So we were given that the men were randomly selected, so we can assume that they're a representative group of all men. 10 is certainly less than 10% of all men. And then you don't have to check this condition about the data being paired, but it's not a bad idea that if you're going to pair them to explicitly state what they're paired by, just so you're making sure that you do in fact have paired data. And then you need to look at the distribution of your sample. So I'm partial to the normal probability plot, particularly for small sample sizes. When you make the histogram for something that only has 10 individuals in it, often the histogram doesn't really look that great. It doesn't appear to be unimodal or symmetric. So for a normal probability plot, what you're looking for is that it's reasonably linear. And I just personally find them easier to work with. So you're welcome to make a histogram and show that. You would be looking for that histogram to be reasonably unimodal and symmetric. But again, for smaller sample sizes, you might not see that happen. So here's how you do a normal probability plot. So if you go ahead to your stat plots and turn one on, the normal probability plot is this very last one out here. It actually kind of looks like a scatter plot almost. So again, and then you're just telling it, I put my list of differences into list 1. So this will give you the normal probability plot, and then you can just go ahead and zoom 9, and that's what that plot looks like. So again, you're looking for that to be reasonably linear. And again, with a sample size of only 10, there's a lot of wiggle room here. And any plot you are going to reference, you should also sketch there. So it's not going to be sufficient to just say it without showing it. So all of our conditions are met here. So we're going to go ahead and do a matched pairs t-test or a paired t-test. The degrees of freedom here, remember, we're really doing the mechanics of a single sample t-test. So we really have essentially one sample of 10 men, where for each one we have a single value. And so your degrees of freedom is going to be your sample size minus 1. And then we're going to go ahead and use an alpha level of 0.05. All right, and then for the mechanics, so I've here just go ahead and made my list of my before, minus, after pulse rates. So these are our changes in pulse rates right here. And notice that direction does matter. We did have one person whose resting pulse rate was actually higher after exercise, so that's going to show up in our list as a -1. And now we have our summary statistics, so we have the average of our list of differences, the standard deviation of our list of differences. So that subscript is just indicating that what you have is a list of differences. And then what we need now in order to calculate the p-value is we need this distribution, which would be the distribution of all possible x bar sub d's. So if we took another sample of 10 men, had them do the same thing, found an x bar, and then kept plotting those. So we need the standard deviation of this distribution, which is the standard deviation for all x bars, which is going to be the sample standard deviation over the square root of the sample size. The fact that we are using the sample standard deviation in place of in this formula is what is causing us to use a t-distribution rather than a normal distribution. So for a procedure that deals with means, you're always going to use a t-distribution rather than a normal distribution. So this gets us the standard deviation for this distribution. Then we can go ahead and calculate t, and then we can go ahead and calculate our p-value. So hopefully, again, you can recognize that p-value is really low. So our conclusion then is we've got a p-value that's really low. It's lower than any reasonable alpha level, so it's certainly lower than 0.05. So we're going to reject the null hypothesis and conclude that we have convincing evidence that this kind of exercise can reduce resting pulse rates in men. All right, and then the other question that we were asked here is how much of a difference? So we did conclude that there was a difference. So that follow-up now is, well, how much of a difference is there? So what you're being asked to do here really is to go ahead and construct an interval that tries to predict that difference. So for our interval then, to answer that question by how much, we're going to do a paired t-interval. We're going to use 90% confidence because we had an alpha level of 5%, and we did an upper tail test. So we need to make sure we did only a one tail test. So we have to take off 5% for each tail since our alpha level was 5%. So we're going to go ahead and use 90% confidence level because that matches the alpha level for our test. I calculated t star for 90% confidence. That's just right on your calculator. We're using 9 degrees of freedom. And then we're just going to plug into our formula for creating the confidence interval. So that formula is the same all the time. It's your observed statistic, which in this case is our average difference. And then our margin of error here is going to be our critical value, which is in this case our t star, times the standard error of our statistic. So that standard error is the same as it was up here. So I'm just pulling that number from up here. And that'll give us this confidence interval here. And then we're going to go ahead and interpret that. So we did a 90% confidence level. So we can say that we're 90% confident that this exercise program can reduce resting pulse rates by an average of 1.37 beats per minute to 3.63 beats per minute for men. This is key here because we're talking about the average change, because we took that list of differences, the list of changes in pulse rates, and we found the average of that. And this is a prediction about that average. So make sure you have this in that conclusion.